Let's continue examining the code for real-time plotting of EEG data. The local variable, PLT, is created and destroyed, but the field PLT_CTX persists across frames. How does the field PLT_CTX preserve the plot info? Our code is inspired by the GitHub repository eplot. The struct plot is responsible for plotting the real-time EEG data, where MEM is a reference to something of the type memory. In our current application, when a plot is created and destroyed, the object that MEM field points to still lives. This is how we preserve information about a plot across frames. Please note that we do not preserve the range of the x-axis values. If we do, we are going to have something like this. The default trait is implemented for the struct memory. For the struct plot, the new method is responsible for structure instantiation. The show method does the job of painting our data using the resize container. As in the previous video, a painter is allocated for the resize container. Then a rectangular area is obtained for the actual plot, excluding the y-axis area. A frame is drawn for this area, and data points outside the area will not be drawn. The data are converted to fit the plot, and drawn. Let's explore how the PLT_CTX field stores plot information step by step. In the main function, we initialize our application struct by calling the myAppNew function. This function is called once at the start of the program. The update method is called repeatedly for repainting, creating and destroying plots while preserving the PLT_CTX value. Let's delve into the details of the PLT_CTX field. This is the default trait implemented for myApp. The PLT_CTX field, responsible for persisting plot information across frames, functions as a hash map with an initial empty value. If we aim to create 8 plots, the PLT_CTX field evolves as we add key-value pairs to the hash map. Each plot is associated with a unique key, such as P1, which creates a memory instance for that specific key. As the hash map grows, it accommodates all 8 plots. When the update method is called subsequently, the existing value is retrieved for a key like P1 instead of creating a new one. Notably, the adjust y field was overlooked. To alter the plot appearance, we can modify the hash map. For instance, the setYRange method adjusts the y-axis range of the memory instance to fit the data, ensuring this information persists even after the plot instance is removed. Let's run the application to observe its functionality. Let's add ticks to the y-axis. The code in green calculates the tick values, converts these values to screen positions, and draws the ticks based on these positions. Finally, the text is drawn alongside the ticks. Zooming in our current situation involves changing the values of the start and end points of the y-axis by detecting mouse scroll. If the mouse cursor is within the plot canvas and the scrolling value is non-zero, we need to calculate the amount by which we adjust the range for the y-axis. When the cursor is at the crosshair position, we anticipate that the end value of the y-axis range will change more than the start value. Pause the video to understand how this is achieved. Let's now run the application. Let's explore how dragging works. First, we extract the pointer's position when the widget is clicked or dragged from the response. This maps the Y component of the position to the data range on the Y-axis. A similar operation is performed on the old position. The difference between the new and old positions is used to modify the start and end values of the Y range. Finally, the last position field is updated. Now, let's run the application. Let's compare the code snippets for zooming and dragging. The response struct has a method named interact_pointer_pos, while the pointer state struct has a method named interact_pos. Both methods detect the mouse positions. We have previously encountered the response struct when adding a button widget to the user interface, which returns a response instance. The interact_pointer_pos method returns the wrapped position when the widget is clicked or dragged, or none if the widget is not being interacted with. The input method for the UI struct provides read-only access to the shared input state. It takes a closure and returns a type determined by the closure, such as an option type or a Boolean type. What would happen if we replace the position captured by the interact_pos method implemented for response with the input method implemented for the UI? Let's compile and run the application. It does not work the way we expected.